Did you know that the McIntosh MC2300 Power amplifier, which was sold between 1971 to 1980 for a price of $1,500 or about $8,200 in 2024 money, and was rated at 300 watts per channel into 8 ohms at not more than 0.25% THD, and had a frequency response from 20 Hz to 20 kHz of +0 to -0.5 dB, and weighed in at 128 pounds. Has its own Wikipedia page. Yes, indeed. In my research for doing this video, I discovered the McIntosh MC2300 has its own Wikipedia page. How many other amplifiers have their own Wikipedia page? If you have some, let me know in the comments. That would be kind of interesting. But the MC2300 does, and that's probably because it was part of the Grateful Dead's infamous Wall of Sound, and that has its own Wikipedia page as well. So this belongs to a good friend of mine who said, hey, if I get it over, will you review it? And I said, sure, I will do that. It did have a few issues I found. They turned out to be sort of minor, although one of them was a little tricky to find. I'll have a tour of the front and the back, and then we'll take the cover off the top and the bottom, and we'll see what's going on there, and then I will tell you what I thought after listening and using the MC2300 Power amplifier. So right off the bat, when I hooked it up to my analyzer, one of the channels was acting up. The distortion would go up to several percent, and then it would go back down. If I wrapped it, it would go away, and with the top cover removed, I wasn't able to find anything, so I had to have a neighbor come over and help me turn this on its side so I could get the bottom cover off. And the nice thing is about having the bottom cover off is that I was able to take some pictures, which I will show you in just a little bit. And I found out the problem after a little bit of dinking around, and it turns out there is a stereo mono switch, and apparently over the years it had just stopped making good contact. Sprayed some cleaner lube in there and worked it a bit, and no problems after that. Plus, when I had the bottom off, I could tweak the power meter potentiometers, and you'll see where those are in a little bit as well. Now, this is more of a professional amplifier, although it was certainly able to be used in the home. It has 2 fans that will come on when it reaches a certain temperature level, from what I can tell. And it did come on during testing a little bit. It's really not that loud, and it does go away on its own, reasonable amount of time once it's cooled down a little bit. Now, as far as running it, it never really got hot to the touch anywhere, but I guess those fans just like to help make sure that everything works okay. As far as I can tell, it's original, other than it kind of looks like the output transistors, and there's a lot of them, were replaced at some point in time. It's just there was some labeling on the boards that the output transistors are mounted to, and just kind of the way the heat sink grease kind of leaked around the edges. I don't know if that's how McIntosh did things then, but it just seems a little suspicious, although the driver boards didn't look like there were components replaced on them. So I don't really know that the output transistors were replaced. The main filter capacitors looked to be original, as did all the other capacitors that I saw poking around in it. So we'll get more into that in just a little bit. So right now we're going to do a little tour of the MC2300. We'll look at it from the front and the back, and then we'll look at it from the top with the cover removed and from the bottom with the cover removed. And then, of course, there will be a lot of data, and there will be my listening experience with it and just using it. Now, the thing I should point out that this is the part 2 of using the QuantAsylum QA40x audio analyzer. And so I'm going to go into more detail on how I do my settings and setting up to do the different measurements. So every measurement that I made, I believe I show how I set up and maybe my thinking behind it, and just kind of how to use the QuantAsylum analyzer to make these measurements. And if that doesn't interest you a lot, you can fast forward through the video. There should be plenty of chapter breaks between each measurement to help you, fast forward through some of the stuff and get to the end quicker if you so desire. So with all that said, let's start into the MC2300. This obviously is a closer view of the McIntosh MC2300. You can see that it's designed to be rack mounted, and we do have our on-off switch over here. Here is a pilot light that will come on when the unit is powered on. Here is our meter range switch, and we can turn the meters off as far as action-wise. I don't know if it kills the lights. I never turned them off, but you can also set it for either 0, -10, or -20. When it's on 0, the 0 dB point would be 300 watts. When it's on -10, the 0 dB point would be 30 watts. And if it's set for -20, the 0 point would be 3 watts. And these are our gain controls. If you're running it as a mono block, the right channel is the one that adjusts the gain for that. They're actually in the positions that I needed to get them balanced for the testing that I did. This obviously is the rear of the MC2300, and the first thing that jumps out at you are these big fans right here. They're actually rather quiet when they come on, and they basically cool half of the output transistors, heat sinks, one for each channel. This guy right here is our AC input. Now, neither I nor the owner had the original McIntosh power cord, so I used an 8 or 10 foot extension cord and had to use a grounding adapter, I call them, those little adapters you plug in the 2 pins so you can connect something with 3 pins to it and bend the grounding lug tab away. There is no ground here. That's really wasn't anything right there for grounding. And then it worked just fine. We have a 20 amp circuit breaker. Now we have a bunch of taps. I've never seen an amplifier that had taps for this many output loads. We go all the way down to 1/2 ohm. That's pretty impressive. And you can see it tells you what your load impedance is as well as the output voltage would be. That's mainly for PA systems. I do have my spade terminal lug adapters to banana here that I use for making it easy to test. Here are our unbalanced inputs. If you were using this as a mono block, you would just hook up the right channel and you would set the switch here to mono. This switch did give me a bit of problem. It turns out that the left channel, I believe, was showing intermittent high distortion up to several percent. And once I had the bottom off and was able to spray some cleaner lube into that, it went away. And I didn't know that was causing the problem. It was just kind of dinking around with stuff. I was able to figure out that's what the problem was. And if you want to run in mono operation, here we have the instructions on doing so. Now, one of my little nits, and I bring this up later in the video, is that if you were standing behind the output and plugging in and your rear of the amplifier, or this side of the amplifier, was sticking towards the speakers, your left speaker would be on this side and your right speaker would be on this side typically. And they have it the other way. So you kind of got to pay attention. For some reason, McIntosh always does things a little bit differently with the position of the right channel and the left channel outputs in relation to where your speakers actually are. This is what it's going to look like when you remove the top cover of the MC2300. We have our 2 cooling fans here. There are 8 heat sinks with 3 output transistors on each heat sink. Now the amplifier operates in class B mode and all the transistors are NPN. Here's our power transformer here, and our 2 auto formers for the outputs are here. The power meters are underneath these incandescent lamps. We have another view. So this is another view of the inside of the MC2300 from the top. You can see that we have some thermal switches here for the fans, and this kind of just gives you a little bit closer view of the output transistors. And here is one more view, and this shows the 2 driver boards here for the output stage, and they are removable. From the bottom you can see they're socketed here, and if you remove some screws you can get these boards off. Now, the one thing I noticed was this heatsink is different than this heatsink. And you'll see in a little bit that I think at some point the output transistors may have been replaced. I can't say that for sure, but the only evidence I had there may have been a repair happening at one point in time was that these two heatsinks were different. So this is what the MC2300 looks like from the bottom once you take off that bottom cover. And the thing that stands out the most are these four big capacitors. They're 39,000 microfarad at 40 volt each. Now, it turns out that the power transformer has two windings that are each for the power supply, one for the right channel, one for the left channel, and then they use one of these big caps for the plus 40 volt supply and then the minus 40 volt supply. So it's kind of like a dual mono power supply approach, although both windings are separate on the power transformer. This right here would be where the AC comes in, and then we have our speaker taps here. And if you go over here to the front, this switch right here is for the different meter positions, and these two are our gain pots. Now, this board right here would be the preamp board, and this board right here is the meter adjust board. There are two pots you can use to adjust the accuracy of the power meters. One's right here and one is right here. And this kind of just tells you what it looks like. Now, if you look here, all along here, there are different numbers, and somebody had little pieces of tape and they wrote numbers on here, and that's why I think this thing was taken apart or maybe repaired at some point in time, because I doubt McIntosh had sent the unit with these, but maybe they did. And here is just another view showing a close-up of what's kind of going on. It may not be obvious, but this is the top cover of the MC2300. And one of the neat things McIntosh did with their vintage gear was to give a block diagram as to electronically what's going on, as well as some basic specifications. So right now I have got the MC2300 on, and there is no signal going into it at the moment. I've got both of the gain controls set to a maximum, which is about 10 on the dial. Now, it has been on for at least, I'd say 25 minutes, just sitting there with noise going in, and it's hooked up to 8 ohm loads, and the QA403 is also on. What I kind of wanted to do is show you how I set things up. Now I have a regular panel that I use, and you can see all the things here. You can add or subtract to that. And the first thing, we'll start up here at the top. I usually use a sample rate here of 96. And we'll start off with 42 dB of attenuation just to be on the safe side. Also, you can see my display settings are set for frequency, input, and then I've got both left and right for the left and right channels to be displayed. I've got it set for DBR, and the X log, that's the frequency span from like here to here. That is set, let me right click on it, to be 20 hertz to 20 kilohertz. All right, so the other thing I want to do is I want to right click on the THD window, and I want to set it so that my start frequency is 10 hertz and the end frequency is 45 kilohertz. That's just kind of a standard setting that I use. And if I come over here and I right click on Gen 1, it's showing a level of minus 9.2. I'm going to move that to minus 20 because we've got the gain set for maximum. I'm not really sure how much gain this amplifier has, but we should be okay if we have the attenuator set for 42 dB and this at minus 20. Also, I usually use half a dB increments for this amplitude knob sensitivity. As I start getting near the max power, I'll change that to 1/10 of a dB. So now I've got that all set up, and I'm going to go ahead and hit run, and we'll see what kind of signal we got going on. So you can look here, and you can see we've got 39 dB of gain. I don't want to test it using 39 dB of gain. It's kind of a nice figure of merit, I guess. for the amplifier that it could do 39 dB of gain, which is pretty good. We're also putting out 10 watts. So I like to set the volume control for about 25 dB of gain. I used to use around 29 dB of gain, but the king of measurements, according to at least my world, would be Amir at Audio Science Review, and he recently changed his gains for 25 dB when you have the ability to change the gain of the amplifier. So I'm going to go ahead and adjust the left and right gains till I get about 25 dB. Okay, so the gains are set pretty close to 25 dB, and in case you're wondering, the left gain control's at about 5 and the right gain control is set for 6, so they're off a little bit. And the next thing I want to do is adjust so that I have 5 watts into 8 ohms, and I'm going to adjust the amplitude up until I get pretty close to 5 watts. Okay, so I've got close to 5 watts. Let me move it up one more, half a dB, so we're at pretty close to 5 watts. I can probably tweak the level just a little bit if I put this maybe a tenth of a dB less, so we'll call it minus 9.1. It should bring the right channel closer to 5 watts. Let's see here. So it's 5. This is 4.97. It's a little low, so I'm going to go ahead and tweak the gain of the left channel just a tad. Okay, I've got them adjusted pretty darn close. In the grand scheme of things, you don't have to be that close. But it's just one of those things that I think most of us do to try to get our numbers as close, mainly the output power. So we're basically putting out 5 watts into 8 ohm loads with 25 dB of gain. You can see the right channel SNR is what, 79, and we're a bit better than 74 dB for the left channel. And the THDs are better than, we'll say, 0.04%. THD plus noise is what, minus 68 dB or better. So that's kind of the basic setup for this. And if you want, you could put on a different window. Oh, I almost forgot. So what I want to do, it's only 5 watts. I usually set it to 18 dB, and usually things will improve a little bit. There's kind of a little trade-off between the SNR and the THD, but it just looks maybe a little bit better on the SNR, probably not that much different. And so I just like to bring the attenuation down to the minimum that I need to, and so you can see that it's looking pretty good overall. So if you flip in the rectangular window, you can see it might make a little difference, or, you know, there's flat top, there's other ones, but overall I like the Hahn window. That's worked best for me for the THD measurements. Now you can also change your FFT size. I started off with an FFT of 128K. I probably don't need that. You could probably go down to 64K if you wanted. It's not going to make a big difference here for the THD and frequency for this span, but it might speed up the measurement a little bit. But I think that the speed is pretty good with the 128K FFT. So one thing that I want to do is I want to go ahead and save the setup that I have right now. And I've already done that, but I'll show you the steps. So File, Save Settings, and I call it MC THD 5 watt 8 ohms. So I'm going to go ahead and save that. It's already there. Do you want to replace it? Of course. Okay, so now what I'm going to do is I'll close one of these windows to create an open space. Now I'm going to right click here. I'm going to say uncheck all. And then the ones I want for measuring frequency response, which is what I'm going to measure next, are the System Gen EX. And I'm going to go ahead and put the FFT and the averages up as well. So I'm going to hit OK. So I've got those 3 things going on. The other thing is, if you remember the power level that we had previously at the THD for 5 watts at 1 kilohertz was minus 9.1. So what I want to do is click the frequency response generator, and then I'll right click and I'll set this to minus 9.1. So that means we'll be at about 5 watts into 8 ohms, at least at 1 kilohertz. If we're flat, it's pretty much going to follow that. And the other thing I want to do is we can be at 18. We're still at, is set the attenuator for where we were before. Sometimes you can vary this a little bit. If you have a wide frequency response, you may have to go to 24. But overall, it probably is going to be good at 18 dBV. And then I'm going to go ahead and hit run. And if you look real closely here at the top, you can at least see the trace there. And what I'm going to do to center that is I'm going to click the plus and minus 1. And so that kind of brings it in the center. Now I like to have my center trace, the left trace, it usually is right here at 0 dBr. So I can come over here, right click, and set 1 kilohertz level to 0 dBr. And there we go. The other thing I can do is I want to expand that. I can drag over the area I want to expand, and we'll do it that way. And so now we have an expanded view. It shows a very good frequency response. We're down 0.15 dB or so at 20 hertz, and at 20 kilohertz we're down maybe a half a dB. So overall, the frequency response looks really good. The channels are pretty well balanced the way I adjusted the gain. So that is kind of how you go about measuring the frequency response. So I should point out that the frequency response at the maximum rated power would be plus 0 to minus 0.5 dB. So we're not at the max rated power, but we are pretty much meeting the frequency response. Right now I'm going to measure the output impedance, and in order to do that I want my output power level set for 1 watt. That's based on the old output impedance measurement, and so I set it for 1 watt. I'm going to go ahead and load the THD 5 watt into 8 ohm settings that we did a little while ago, and then I'm going to go ahead and hit run, and I want to adjust the amplitude down here to have about 1 watt. So I'm pretty close to 1 watt. I'm just going to bump it up a tad more so I can come over here and set this to minus 16.1. That'll get us just a little bit closer to 1 watt. So there we go. Doesn't really have to be. And I'm going to put my attenuator to 12 dB because we don't need it at 18 since we're just going to run the sweep at 1 watt. Now the other thing I want to do is come over here to the THD and right click on that, and I want to set my start frequency for 10 hertz and end at 45 kilohertz. So now I'm going to go ahead and save that. We're going to go ahead and save that setting and call it THD at 1 watt 8 is kind of how I name it. And then what we're going to do is stop and hit automated test and come over here to power output impedance. And what I want to do is have the power level set for what I found 1 watt at 1 kilohertz to be, which would be minus 16.1. And our start frequency is 10 hertz. We're going to go to 22 kilohertz, 200 hertz step. I'm going to do 5 points per octave. I don't think I need 8. And the load that I'm using is 8.06 ohms, close enough. And then this secondary load setting, well, ideally you would want an open circuit, but the QA40x software doesn't allow you to just say open circuit, so it does allow you to go as high as 1 mega ohms. That's pretty much an open circuit. And I'm going to go ahead and plot the right channel. I'm going to hit OK, and it wants to make sure that you are indeed into your 8 ohm load. I'm going to hit OK, and in a little bit it's going to ask for me to set the impedance to 1 mega ohm. Okay, so we got the message to set the load impedance to 1 mega ohm, and what I'm going to do is disconnect the input from the amplifier, or the output of the amplifier rather, that goes into the load, and just leave it kind of standing out so it's basically looking at an infinite output impedance. I just did that. I'm going to go ahead and hit continue. Okay, it just finished doing the output impedance run, and what I'm going to do right now is I'm actually going to connect my load back up, because you won't believe how many times I have gone to my next measurement with an open circuit for the load. So I'm going to go do that right now. So I'm going to go over here and change the title to MC2300 output impedance or whatever you want. I'm going to change the frequency span, and that's one of the reasons that I went down to 10 hertz. So I'm going to say the minimum value is 20 hertz and the maximum value is 20 kilohertz. And now what I can do is I can zoom in on this area. So I can come over here, and for the Y1 max, I can call that, we'll say 1. And for the minimum, I can say 0.6. And that's kind of how the scale is expanded a bit. And in case you're wondering, there is a spec for damping factor. And the way you get damping factor, let me see if I can get the calculator up. So I pulled up the calculator, and basically the damping factor would be the output impedance, which is 8.06 divided by the output impedance, which would be, let's say the best case is right here. So that's about 0.65 ohms, we'll say. So let's put in 0.65 ohms divided by 0.65, 12.4. So there is a specification for damping factor, and that is using the 8 ohm tap. It should be better than 14. And we're really not that far from 14, 12.4. That's really pretty close in the grand scheme of things. If I come over and you look at, that was for the left channel. If I look at the right channel, it's closer to about we'll say 0.74 dB if we use the value at 1 kilohertz. Let's see what that gives us. So we have 8.06 divided by 0.74 equals about 11. We'll just round it to 11. So it's off a bit, but it's not too far off. It's at a damping factor of 14, so we're between 11 to 13. So now I'm going to measure the crosstalk, and in order to do that, I'm going to go ahead and recall the setting for the THD at 5 watts into 8 ohms, this guy right there. And note the power level is minus 9.2. And what I'm going to do is come over here to the automated test and go the amp crosstalk automated test. And I'm going to go ahead and set this stop level to minus 9.2. And I'm going to go ahead and start it, I'll say 3 dB up, so it'll be minus 12.2. Now, I'm going to throw this measurement out. I just usually display one at minus 9.2, which is 5 watts into 8 ohms for the active channel. But the software doesn't give you the option just to do one power level. So if you wanted to sweep the crosstalk over a range, you could, but I'm just going to start off at minus 12.2 and go to minus 9.2. Start frequency 10 hertz and then to 22 kilohertz, 200 hertz per step, log step, 5 points per octave. I'm not using this this auto set input range. I'm going to set the attenuator for 18 dB, and that should be adequate to run the test at because it's a fairly flat amplifier. And I want to measure the left to right and the right to left crosstalk. So I'm going to go ahead and press OK, and then we'll come back and see how it did. Okay, we have finished running the crosstalk measurement. I should point out that the fans came on during this measurement. So the first thing I'm going to do is create a title, and we'll just go and the next thing I'll do is I'm going to do the x-axis from 20 hertz to 20 kilohertz. There we go. And I'm going to get rid of the minus 12.2 dBV traces. So I come up over here and I select this first trace, go to trace, delete selected trace. Then I'm going to come over and do the other minus 12.2 and delete selected trace. And there you can see our crosstalk, and it goes anywhere from about 52 dB, 53 dB to as good as about, we'll call it 68 dB. Right now I'm going to set the MC2300 up to measure its specification of 300 watts into 8 ohms. And in order to do that, I've put the taps on my loads into the position where they're minus 18.1 dB down. So what I do is I right click on dBV and I enter minus 18.1 for the input gain. And what I'm also going to do is move the attenuator to 42 dB. It's just for safety. I can change that as I need to. And I've recalled the 5 watt into 8 ohm state. What I'm going to do is set this generator 1 to about, we'll say 4 dBV. And you can see now that it shows that our input gain is minus 18.1. So our actual power displayed will be the real power. I'm going to go ahead and hit run. And we can see we're not at 300 watts. I can increase the power by increasing the amplitude here a bit, and we're at 150 watts. So if I add 3 dB to that, I could come over here and we'll just say 8. We'll just change that to 8, and we should be close to 300 watts, 250 watts. We can increase this a little bit. I should point out the fans are not on yet. I do expect them to come on. I'll increase this by half a dB and actually another half a dB. So we're pretty close. We're just a tad over 300 watts, close enough for government work, we'll say. And the other thing I'm going to do is increase the Y minimum axis so that we get kind of a more of a vertical display here. It's expanded a little bit. And I can bring my attenuation down a little bit. 36 dB is all right. We'll try 30 dB. So it will just improve the measurement accuracy a little bit. Now, one thing you can see is our gains are pretty darn close. The SNR of the right channel is, 15 dB better than the left channel. However, the THDs are almost identical. They are, we'll call it 0.11%. So we are meeting the THD requirement. And the other thing to note, let me go ahead and turn off the left channel. You can see there's the right channel, and I'm going to go ahead and click on the left channel, and that's what that looks like. And the other interesting thing I can do is I can come over here and hit Visualizers THD bar graph, and I'll kind of move that towards the center. Go ahead and click on right channel, and this shows the THD. You can see that the third or odd harmonics are greater than the second or even harmonics, which is kind of what you would expect for a solid state amp. So I'm going to go ahead and turn that off. And this is kind of how it's looking now. I could see how much more power I can take before it gets really, really ugly, or I start getting past the specification here of, or before I hit, there's half watt. So we're over 1%, at least the right channel. So we're 0.6%. So we're above the spec, and we're at about 324, 28 watts. So we'll just call that our max output power into 8 ohms. Right now, I'm going to measure the THD versus frequency versus output power levels. And in this case, the output loads are going to be 8 ohm loads. And even though this is a 300 watt amp, the most power that I'm going to have come out of it is about 200 watts. So what I do beforehand is I set my load up. So I'm using the 2.5 dB tap. You can see it's set here. And once again, if I click over here on dBV, I can set the offset to minus 2.5 for the input gain. And the other thing I'm going to do is I'm going to click over here onto THD and make sure my frequency range is 10 hertz to 40 kilohertz. And I've already gone in and figured out what power level I need for the input signal to get me to 200 watts and 8 ohms. In this case, it is 7 dBV. And then I'm going to go down until I'm around 3 watts or so. It kind of just varies on how many points you want to take, but the 3.3 watt at 1 kilohertz is around minus 11 dBV. So I'm going to go ahead and use that in my settings, and I'll show you in a minute. So like I said, I've got a minus 2.5 dB input gain set. And the other thing is I'm going to keep the attenuator at 36 dB. Now I'm going to go ahead and click over to the automated test. And I'm going to come over to this automated test, which is amp THD versus frequency. I'm going to go ahead and click on that. And this is where I set my levels. So I'm going to start at the lowest signal level, which would be minus 11 dBV. So I'm going to set this to minus 11. And the stop level is plus 7. And what I have found is that I like to be a little bit higher, and I'm going to say 7.6 than plus 7, because sometimes this won't give me the last step for whatever reason, just the way the software works with rounding out. It might only go to plus 4. So if I give it to plus 7.6, usually I will be able to hit the plus 7 that I want. And it's going to be in 3 dB increments. My start frequency, 10 hertz, stop frequency, 22 kilohertz, 200 hertz step size, log step, 5 points per octave, right channel. And I don't use this input offset range. You could, and it'll increase the attenuator, but I like to keep my attenuator fixed here. You're going to lose maybe a little bit of resolution at the lower power settings, but I think it's probably good enough for the kind of stuff that I'm going to do. So I'm going to go ahead and hit OK, and it will start running. And I will come back once it's all done and it's shown the plot that we get. I went ahead and added a title, which is right here. I also went and I changed the scale for the x-axis, so it starts at 20 hertz and goes to 20,000 hertz. I also went ahead and changed the Y1 max and minimum values. The max value I set to minus 40 and the minimum value I set to minus 80. I always use the dB level rather than the THD percent. I usually plot in THD percent and dB. You can also do THD plus noise if you want. Now it looks pretty good. Remember, the spec was 0.25% THD, and that would be about somewhere in here, around here would be probably about 0.25. So for the most part, it's meeting that. Over here with a minus 5 dBV input, which is about, I don't know, about 13 watts, 12 watts, something like that. It does exceed that a little bit, and here at 20 kilohertz, it does exceed that. But overall, we're no worse than 0.5% THD at 200 watts. So overall, it's doing a pretty good job of meeting its requirement. Not 100%, but pretty good. Right now, I'm going to test the MC2300's multitone response. And one thing I want to do is probably put this over to 24 dB of attenuation. And I'm going to go ahead and hit multitone, and I'll right click on it. And usually a good setting is minus 12 for the input level. And the other thing I'm going to do is get rid of all the SNRs and the THDs. And really all I need is the volts and the gain. I don't need any THD plus noise. We'll get rid of that. So it's kind of will give us an indication of where it's at. So I'm going to go ahead and hit run. And what I'll do now is I'll right click on dBr and set the 1 kilohertz to 0 dBr. And that way it brings everything up to 0. And we're still set at 25 dB of gain. I'm going to increase the input signal level to get a little bit more power. I like to try to get close to 5 watts. That's not always something I'm able to do. We'll see what happens here as we start increasing it up. Our gain drops. So I'm going to go ahead and we'll stick with that input signal level, maybe one more, half a dB. So we're pretty close to where we started at 25 dB of gain, and we're about 4 watts. Now the other thing we can do is come over here and lower our y-axis, the bottom part here. So clicking on this guy till we can get as much vertical resolution. And so what you normally do is start seeing where the noise is. Now both channels are about the same, and I'm going to say that we're minus 70 dB down. So if you look at it, you just divide this number. So if it's minus 70, you divide it by 6 bits. That comes up with like 11.7 bits, and it might be as good down here as maybe, we'll say 75. So, maybe 12 bits. So we've got between 11 and 12 bits of distortion free range is the way that it's rated. I should mention that you may want to play around with the sample rates. I probably wouldn't go less than 96K, and the FFT that I'm using is 128K. You also can play with your attenuation to try to optimize the distance between 0 and your noisiest part of this multitone response. And the other thing you can play around with is the windowing, and whichever one gives you the best results, I guess that would be what I report. But I pretty much am almost always using the Hahn window, and it seems to do a pretty good job overall. But you could try another window and it might give a better result for the distortion-free range. Right now we're going to look at the system noise of the MC2300. Now there isn't a spec for the hum and noise, which is what we're going to look at. There is a spec for what it is at the maximum rated output power, and I'll show that in just a moment. But in order to get there, I do have both of the inputs to the MC2300 terminated into 50 ohm loads, which I normally call a short because for audio purposes that would be a short. Also, I set for dBV here, and the frequency range is 20 hertz to 20 kilohertz. Also, I'm going to put the attenuator at 0 dB of attenuation. If there's a lot of hum, it may force me to go to +6, but normally we can get away with 0. I'm using a 96K sample rate, and the FFT is 128K. And across my top, the only thing I'm displaying is the RMS volt. So I'm going to go ahead and hit run, and we'll see what we're looking at. And what I'm going to do is just go ahead and stop the trace. And we are minus 60 dBV down, or maybe minus 65 dBV down. This would be at 60 hertz. This guy's at 120 hertz and 180 hertz. So we are better than 65 dBV down. Now, in case you were wondering what it looked like when we had 300 watts applied, let me go ahead and bring that up. And this was a trace from that. And if you look, this is 0 dBV, and the hum and noise for the left channel, it starts at maybe, we'll say 80, 85 dB, maybe almost 90 dB down from the peak here. And the right channel is better than that. It's anywhere from, we'll say 105. And, it might go a little bit higher there, but we'll say we're better than 100 dB down. And the spec was that the hum and noise should be better than 90 dB down. And I forgot to mention that this is with the loads being 8 ohms. Right now, I've set up to look at the two-tone IMD distortion. In this case, the tones I'm using are 19 kilohertz and 20 kilohertz. You set those down here. You right-click on Gen 1, and that guy I set for 19 kilohertz at minus 13 dBV. And then the Gen 2, I've set for 20 kilohertz and minus 13 as well. Now, what you can do to try to get your output power, you adjust both of these the same. So if this guy increases by half a dB, then this guy's going to increase by half a dB. I've set the volume controls to give me about 25 dB of gain, well, almost 26 here. And I don't have a lot displayed as far as the information, mainly just the power. And let me show you what else I have set up. So for the dBV, I've set it that there's no input offset, and I've set my load impedances. Also, I've set the attenuator for 24 dB. That's a good place to start. If you can go down to 18 dB, you can do that. or you could go up if you need to. And my sampling rate is 192K, and the FFT I'm using is 128K. So that's kind of the setup. I'm going to go ahead and get rid of the left channel. Oops, I got to start running it again. So let me run it. And I'm going to go ahead and turn off the left channel. And you can just see the right channel. And kind of what you're looking at is the sum and difference of the 19 and 20 hertz tones. And probably the most important one is the difference, which would be at 1 kilohertz. You have some up here around 38 to 40 kilohertz right here. And let me go ahead and turn the left channel on, and you've got a higher noise level for the left channel. You can just kind of see what's going on with it. It's varying around a bit. And if I wanted, I could dump the traces. So let me stop the trace. And if I wanted to export this data, I could go to File, Export Data, and I could save it as a frequency series. And it's going to save a CSV file. I'm not going to go ahead and save it, but it will save a CSV file. And you could play with that in Excel. I developed a spreadsheet for 19 and 20 kilohertz tones, and I can dump the data in, and it will give me what the IMD is in percent. If anybody's interested, you could email me, and I could provide that spreadsheet to you. But we'll just say that this is how I do the test. Now, sometimes the two tones might be at 70 hertz and 7 kilohertz. It just kind of depends on the particular amplifier. If it doesn't specify it, I just use these two tones. And in this case, the IMD wasn't really specified as to what tones that were used. There was a specification, and it basically says any combinations of frequencies between 20 hertz to 20 kilohertz, and it should be less than 0.25%. From what I've seen, usually that's the case, and if I get a chance, I will dump it in the spreadsheet and actually see what we get for that. I went ahead and dumped the CSV data that I exported into my Excel IMD spreadsheet, which is set up for 19 and 20 kilohertz tones. And basically it calculated that for the left channel, the intermodulation distortion was 0.00, we'll call it 8%. And for the right channel, it was 0.0002%, we'll say. So it was well better than the specification, at least for those two tones. Since the MC2300 has power meters, I thought I would check to see how accurate they are. Now, this one displays in dB rather than watts. And if you have the meter range set for 0 dB, when you hit 0 dB on the meter, that would be 300 watts. Now, I'm not going to test it there. I'm going to test it at 30 watts and 3 watts. So the minus 10 dB position would give us 30 watts. And I'm going to go ahead and start out with the 5 watt setting that I had before, and we'll adjust the output of the generator number 1 until we get that. I'm going to go ahead and we'll just turn it on and see kind of how close we are to 5 watts. We're pretty close to 5 watts, so I'm going to go ahead and up the amplitude a bit to get to 30 watts. So the other thing, if you can hear the relay clicking, I'm going to go ahead and click the attenuator to 30 dB. And we're at 13 watts. We still have to go up a bit more. So we're fairly close to 30 watts. I could adjust the gain just a tad to get them closer, but we're close enough. So the next thing I'm going to do is I'm going to go ahead and click idle, and then I'm going to hit stop. And what that will do is cause the 1 kilohertz signal, which is what it's set for right now, just to put out 1 kilohertz without the standard pulsing that you normally get when you're actually getting data. So it's kind of just putting out 1 kilohertz. That's great for troubleshooting or testing power meters. And we'll see how accurate we are to the 30 watt settings. So the left channel is dead on and the right channel is off a little bit. So we're pretty close for all purposes. So the other place I'm going to check it is at 3 watts. So I'm going to go ahead and get my setting back for 5 watts. Load settings. We'll go ahead. So we're at 5 watts. And if I drop that down probably 2 dB, we should be pretty close to 3 watts. So I'm just going to tweak it a little bit. We're pretty close to 3 watts. For all practical purposes, this is close enough. So left channel is a little bit more, right channel is right at 3 watts. So let me go ahead and put the unit in idle mode and stop it. So right now it's running, and if I go ahead and hit stop, once I've selected idle, it'll continue to put out whatever the test tone is set up here, which is 1 kilohertz. And let's see where we're at with our power meter. So I set the power meter range so that it's at minus 20 dB. So 0 dB would be 3 watts. And it is pretty close to 3 watts for both channels. So I would say the meter is pretty accurate. I'm not going to test it at 300 watts. You saw earlier there was a circuit board where you do the adjustments, and it's really not practical to do them on these for most people unless you had like a special stand to do that. But I did try to adjust them as best I could while I had the bottom off and the unit was on its side. If it's on its side, that may affect the adjustment a little bit because of just gravity's swing on the meter, but I don't know if that's a real thing, but I tried to adjust it as close as I could at the lower power levels. Right now I'm going to measure the THD versus input power level, and this is just done at 1 kilohertz, but before we get there, what I'm going to do is recall the settings that I had saved when I measured the 300 watts into 8 ohms. So I'm going to go ahead and pull that up. And I've already set up my load so that I'm using the minus 18.1 dB tap, or I'll just say the 18.1 dB tap. So that's built into the measurement. And we have with a 9 dBV input signal going in, we get about 300 watts. It'll be a little bit more than that. Just turn it on for a sec here, and we're a bit higher than that. It's got a lot of distortion, but it'll settle down here once it's running for a bit. So we're somewhere around 315 watts, let's say. So what I'm going to do now is come over here to automated test, and we want the amp THD versus input output level, this guy right here. If you wanted to measure THD plus noise, you could do that. I don't want to do that. And I'm going to start at a very small level. We'll say minus 21 dBV. And our stop level, I'm going to use the 9 dBV there. So that's 300 watts. And we'll say 9. And we're going to do it every 3 dB. And you could change the test frequency if you wanted, but I do it at 1 kilohertz. I'm also going to remove this input, the auto set input range adjustment, and I'm not going to do that because it would improve the measurement, but I just have better luck when I kind of pick an attenuator, and when you start measuring a real small signal level with the 18 dB tap point on the load, it's not going to give you as accurate, but we'll just see how it does for right now. And I want to plot the right channel. So it's going to take data there. And if you wanted to plot the input level instead of the output level, you could do that as well. And so let's go ahead and hit OK. Okay, so this plot here shows the THD, I care about the percent, versus the analyzer output level in dBV, and you could convert this to watts. So at around 9, we're at 300 watts. And I'm going to go ahead and give it a title. We'll call it, so I've got a title written up now, and I'm going to go ahead and zoom in on the scale here. So first off, I want to change the Y1 axis. So I'm going to say the max level for Y1 is minus 45, and then the minimum level we'll say is minus 80. And that kind of gives us a little bit better picture of what's going on. So the right channel shows a worst case distortion at 300 watts of about we'll say it's maybe 0.25%, less than 0.3%, and the left channel is better than 0.08%. So it's fairly good at 1 kilohertz, and as we get lower in power, we're down in the 0.02, 0.03, 0.04, 0.05% THD when you start getting into the really small signal levels. Now, if you had the input adder selected, you could probably improve this, but I think it's a pretty good THD reading, so I'm pretty happy with it. So right now I've adjusted the loads that I use so that they're 4 ohm loads, and I am tapping off the 4 ohm taps on the MC2300, and we're going to look at the power at 5 watts into 4 ohms. The easiest way for me to get there is to go to load settings, and I'm going to load the THD at 5 watts for 8 ohms. So I'll go ahead and load that setting in. And I'm going to come over here and right click on dBV and change this to 4 for the load impedance. And I'm going to go ahead and put the attenuator on 24 because it's possible that I'm going to have a higher output with the input that I'm driving the MC2300 with. So I'm going to go ahead and hit run, and we'll see what it looks like. Well, look at that. It is pretty close to 5 watts into 4 ohm loads. Our gain is down 3 dB about, and that's kind of what I have seen happen when you go from the 8 ohm load to the 4 ohm load. Your gain drops a little bit. So I'm going to adjust the gain up a little bit so that we're closer to 5 watts and we're closer to 25 dB. So I adjusted the gain controls till I got around 25 dB of gain, and then I had to play with the input signal level here, which is about 3 dB less. And so we're about 5 watts into 4 ohms, and this is kind of just so you can compare it to how it looks into 8 ohm loads. Also, I can go ahead and drop this down to 18 dB of attenuation. So if I compare the data that was taken at 5 watts into 8 ohm loads, you can see that it's pretty much the same. Maybe the SNRs are they're pretty darn close for this gain level. The one thing that is different is the signal level going into the MC2300 is about 3 dBV less. But other than that, the rest of the specs look pretty much the same. THD plus noise and the SNRs are pretty close, and the THDs are pretty close compared to where they were at when we had this putting out 5 watts into 8 ohms. So now I'm going to set up to look at the frequency response into 4 ohm loads, and to do that I'm going to go ahead and pull my 8 ohm frequency response at 5 watts, and that would be this guy right here. Remember that it was minus 12 dBV for the 5 watt into 4 ohm load case, so I'm going to go ahead and come over here and set this to minus 12. Then I'm going to go ahead and go over to dBV, and just a purist sake, I'm going to call that a 4 ohm load. The load really doesn't affect anything for the frequency response as far as what it displays here. And we'll go ahead and hit run. If we right click on dBr and set the 1 kilohertz level to 0 dBr, it brings the left channel in the center. We can see that both channels are pretty well balanced. If you compare this to the 8 ohm load case, there's probably just a tad more roll off at the high end of the band, maybe if anything, not even a tenth of a dB. They basically look about the same. They're both down about half a dB at 20 kilohertz, and at the low end of the band, the left channel is down just a tad more. It's maybe 0.2 of a dB here, and it was down maybe a tenth of a dB with the 8 ohm load case. So really not any change in frequency response when using the 4 ohm loads. So right now, as long as I have my 4 ohm loads hooked up, I'm going to go ahead and look at the output power at 300 watts in a 4 ohm loads, and I've already set up my taps on the loads so that I'm down 12 dB in the case of 4 ohm loads. So what I'm going to do is recall the setting I had for the 300 watt into 8 ohm load case for the THD, and that would be this guy. And the first thing I'm going to do is right click on DBV, and I'm going to set this to -12, which is what it is for the loads in the 4 ohm load case, and we're going to set the load to 4 ohms. And then we should be okay, except for one thing. I'm going to adjust this power down about at least 3 dB. I'll say 4 dB, so I'm going to come over here and I'm just going to put that at 5 dBV going in. And let's go ahead and hit run. You'll see this guy change up here. So we're at about 250 watts. You can see that the right channel is got more harmonics there. And I can go up a little bit more on the power. I want to get at 300 watts, which would be the most that this is rated for into whatever load you have, basically. So if it's 8 ohm loads, it's supposed to be 300 watts. If it's 4 ohm loads, it's going to still be 300 watts. Well, we're at 325 watts. Okay, well, we're at 325 watts into 4 ohm loads. THD's looking pretty good. 82, we'll just call it 83 dB. And the THD is better than, we'll say, 0.1%. The spec was better than 0.25%. And you can also see that the gain is around 25 dB. Now, that was after I had adjusted it for the 4 ohm loads at the very beginning when I did the 5 watts into 4 ohm load setting. So the gain hasn't really changed. So it is easily doing 326 watts into 4 ohm loads. And in case you're wondering what the harmonics are looking like, we'll come over here to the THD bar graph, click on the right channel. I always like to give it a little title, and let's center that a little bit better. So you can see that our odd harmonics are, the third harmonic right here are higher than the second or even harmonic, which is often the case, but not always the case with solid state amplifiers. I decided to see if there was any phase difference between the left and right output channels of the MC2300, and in order to do that, I hooked up the same signal, which was 1 kilohertz, into both the left and right channels, and then the outputs were going into 8 ohm loads, and I hooked my scope probes right there at the amplifier where they would connect to the loads. And I adjusted so I got the maximum display, and the amplifier was putting out about 5 watts or so into 8 ohms. This is the Lysigis pattern I got when I put my scope into the XY mode. And it basically shows there is no phase difference between the two channels, at least at 5 watts and 1 kilohertz. So that is just a little piece of information that I thought would be fun to test. Also, I decided to look at the rise time of the output signal, and I just took one channel. I think it was the right channel in this case. And this is my input signal. It's a square wave, a 1 kilohertz square wave. And the output of the amplifier was adjusted so that it's putting out, maybe 3 watts into 8 ohms, just kind of the signal that I put in. And this is the output. So it looks like we have a rise time of 4.77 microseconds, and the rise time of the input signal is about 16 nanoseconds. The cursor is showing the difference between when the pulse kind of just starts to where maybe it gets it pretty close to maybe 90% of the final value, and that delta would be about 7.65 microseconds. So that's kind of just showing the response of the amplifier. I have not done this test before on any amplifiers, so this is the first one. It's just strictly the 8 ohm load. There is no capacitor in parallel with the 8 ohm load. And as I go along, I may do this more, but just for grins and giggles, I thought I would show this result as well. As far as using the MC2300, I only have a few little nits. One of them is I like my power meters to be in watts rather than dB. Ultimately, they give you the same amount of information. Also, with some other amplifiers that I've tested from McIntosh, the speakers, when you're from the back, they're kind of reversed. You'd think the left speaker would be on one side and the right speaker would be on the other side, but they're not. You have to pay attention when you're hooking it up, which you should be doing anyway when you're hooking up connection for your speakers, but that's just a little quirk. And other than that, I mean, it has a fan. It would only come on when it was stressed a little bit during the testing. It's not real loud. If you were playing music, when the fan came on, my guess is you would not hear it. And it's not on all the time like it is, say, in some of the Sound Craftsman amps that I've tested, or the Crown SA2. They're on, the fan's on always, but it's a very, very low level, and you wouldn't really hear it except in a very quiet room. But other than that, it sounds really good. I hooked it up to the Wilson Watt 3 Puppy 2 loudspeakers. I had to have my neighbor and friend Rich come over and help me lift this thing on this cart that it's on, up over some steps over to the listening area, we'll call it, and I hooked it up to my McIntosh C48 preamp, which will have its own review here at some point in the future. And the Wilson Watt 3 Puppy 2 speakers, they sounded great. Before I hooked up the preamp, I terminate the inputs and just listen to see what kind of hum I hear or hiss. And it had a very slight amount of probably 120 hertz hum. Basically, if you were 1 foot away, you wouldn't hear it at all. It was very minimal. And other than that little thing, it had no turn on or turn off thumps or pops. It sounded great. We listened to several tracks of music in the amplifier. It sounded great. Of course, it has the nice big blue Mac meters that many of us love dearly. So the McIntosh MC2300 is definitely an amp, in my opinion, that sounds great. And I think it looks great. Now, if you were wanting to buy one of these, I looked on eBay to see what one of these amplifiers is going for, and they're around $3,500 or so, depending on the condition, plus probably a couple $100 to have it shipped to where you're located. Now, in case you're wondering, was this one of the Grateful Dead wall of sound amps? No, it is not. Usually there was a certain serial number range that those amps fell under, and this isn't in that range, or some of them didn't have a serial number because they made them quickly, whatever. There's a bunch of information on that. But this is not one of those. If it were, you can see from this one that I found for sale, it could be worth 35 grand. So anyway, they are a collectible item, and I kind of see why. It's not easy to move around unless you're really, really strong or have a good friend to help you, get it set up to where the spot is it's going to be setting at. But now, I did not run it as a mono amplifier, mainly because I didn't want to move the stereo mono switch that I had to clean lube around anymore, and I really didn't see much point in doing it. It's not my amp, and I didn't want to take a chance that something weird happened when I was running in mono, which has never happened to me yet. But I didn't really think I need to run it as a mono block. So anyway, overall, it's highly recommended if you could afford it and you can move it around. As always, if you like the video, give it a thumbs up. I suppose if you don't like it, you could give it a thumbs down, but hopefully more people like it than don't like it. That's usually the case, unless I'm talking about speaker wires. There were some thumbs down on that, but we'll just hope that everybody likes the review I did on this. Like I said, it's kind of long because I went into detail about the QuantAsylum QA40x analyzer, and of course, if you have questions about that, you can leave them in the comment section. And a big one, if you have not subscribed to the channel, please do so, as it will help the channel grow and keep me off the street at night. So once again, until next time, have a great day or night.